Hey everyone, welcome to the video. Today we're going to dive into vLLM, a high throughput, memory efficient serving engine designed to optimize LLM inference. By the end of this video, you'll have a clear idea of what vLLM is, why it's important, and why you should use it instead of LLMs. And if you stay tuned until the end, I'll also show you an example of how we can run vLLM in Google Colab. So let's get started. Now, let's understand the use of vectorized large language model or vLLM. First of all, a large language model or LLMs are powerful machine learning models that can understand and generate human-like language. These are the same kind of model behind applications like ChatGPT and Copilot. But there's a challenge. Serving these LLM can be slow and expensive because they are very large and require more powerful GPUs like NVIDIA A100 to run efficiently. So that's where vLLM comes in. Vectorized LLM solve this problem by using technique like page attention and continuous batching, which makes the process much faster and more memory efficient. Let's look at the problem vLLM solves and the benefits of using it. First, the problem. Running large language model is often memory intensive and slow. vLLM solves this by using page attention, which saves memory and allows even larger model to run smoothly. It also uses continuous batching, optimized CUDA kernels, and containerization techniques to make inference much faster. And the best part, its API is very similar to OpenAI's API. So developers can easily switch to open source LLMs without major changes. Now, the benefits of using vLLM. First, you get a faster response time, which makes the application much more expensive. It's scalable, meaning it can handle larger models and heavier workloads. It helps reduce cost because the faster inference means lower compute time. And finally, it gives flexibility. Since it supports a variety of open source LLMs and tools, um, enabling many different AI applications. Let's talk about transformers. What is a transformer? They are the main technology behind LLMs. Here we can see this is our input word or input token. First, our input sentence is converted into input token vectors, which simply means turning words into numbers. Next, these numbers go through something called positional encoding. Positional encoding tells the model where each word in a sentence. For example, take the sentence I love AI. I is at the position 1, love is at the position 2, and AI is at the position 3. Without the positional encoding, the model will only know the word, not their order. It might think AI loves I means the same thing. So, positional encoding adds a number pattern to each word to keep track of their order correctly. Then this passes through um, then they passes this information through multiple decoder blocks. Inside each block, there's a key mechanism called self-attention. Self-attention allows neural network to understand the word based on the word around it. For example, the server took our order. Here, server equal to person. The server crashed during the update. Here, server means computer. By focusing on nearby words like order or crashed, the model figures out the correct meaning and builds a better understanding of the whole sentence. And after all the self-attention process, the transformer generate output token vectors, which are then used for the next steps like generating text or answering questions. So in short, that's what happens inside a transformer. Now let's talk about prefill and decode mechanism. The prefill mechanism takes the input prompt and generate the KV cache for it. Just we'll talk about the KV cache in the next slide, so don't be worried about that. And the decode mechanism which generate the result, producing token one by one and storing the KV pairs. Which means if you look at this video, you can see this is our request or the input prompt we gave, and it first go through our prefill worker, which generate the KV cache for our request or the input prompt. So prefill worker will generate the KV cache for our input word, and it will also generate the next prompt or the first prompt which generated by the AI or the model. So that's what prefill will do, and it goes through the decode worker, which generate the whole other tokens or words of our output. Okay, so prefill, what prefill will do is only generate the input words token, sorry, input words kv cache and the first output prompt, and the rest of the output will generated by the decoder. I mean, rest of the outputs, kv cache is generated by the decoder. So that's what decoder will do. And we'll talk about the kv cache in the next slide. And all these things, decoder and prefill worker is done in the gpu. So that's it. Now let's understand what kv cache is. Kv cache stands for key value cache. This is like the model's short-term memory. When the model starts writing text, it remembers what it has already written and saves that memory in the kv cache. So here, first we have our input, which is artificial intelligence is. So it passes through these layers, which we can see here, um, generated the keys and value for our input token, and it also created the next word, which is the. Okay, so the first thing is our input prompt is here, and it passes through these layers and created the keys and values for the for our input, and also it generates the next the first output prompt, which is here the. So we can say this process is called prefill, like we talked in the previous slide. And after we use our current token to generate the next prompt or next token, like we used the das what kv caches to generate the next word. Like we can see here, first it generated the kv cache for our input, which is artificial intelligence is, keys and values, and then it generated use the next prompt using these key value cache, and we gave the current prompts keys and values to generate the next prompt, which is here future. So that's what kv cache is all about. When we want to generate the next word, the model uses these saved keys and value pairs instead of recomputing everything. Now let's look at the memory waste in kv cache. We talked about the kv cache before, right? So keep that in mind. There are three types of memory waste in kv cache. First one is internal fragmentation. So in this image, we can see that this is our input prompt, and this is the current generated tokens, and these things are the future slots we may use or may not use. And this is another request, which is here. We'll talk about that. So what internal fragmentation is, we keep an extra blank space because we don't know how long the answer will be, right? When we generate when we give the ai or model and a prompt, we don't know how much length output it will return. We keep an extra blank space because we don't know how long the answer will it be. So for example, you expect to write 10 lines, so you reserve 10 pages, but you only write 6 lines and 4 pages stays empty. And here, this is it. This points the internal fragmentation. And the next one is reservation. We save some space for later, but we don't use it right now. For example, if you keep a page marked and like I might need this later, but you never use this during the step. Like we need these slots for the future maybe, but we don't need that at the present, right? So when you generate the token future, we don't need to use any of these blocks, so it will get wasted. So and the last one is external fragmentation. We could have many different sentences of different length, right? Our prompt uh, could be in a different length. Some ends early, some might take a longer time. So the one which end early would leave some space. Imagine you have a notebook where some pages are half written and you can use those half empty pages for new writing. They are wasted. That's what called an external fragmentation. It's due to the different sequence length. So here we only use 20 to 40 percentage of KV cache and others are wasted. So that's a very bad thing. By using page attention, we can overcome all these problems. Before we Before we talk about page attention, let's talk about paging in operating system. Paging is actually works by breaking our memory into small fixed size block called pages and frames. Here we can see that logical memory is divided into blocks called pages and the physical memory is divided into frames. And this page table keeps a list that shows where each page is stored in the physical memory. And when we need to access the memory, we look up the page table to find the needed pages frame. Like we can see if we want the page 0, it's stored in the frame 4. Just by looking at the image we can understand that. So that's the mechanism of paging in OS, and we use this mechanism in page attention, or when we store the key value cache into our memory. That's called page attention. Let's look at that. So here we can see this is how the before generation will looks like, and we have our prompt, which is Alan Turing is a computer scientist, and here we have just like in the paging in OS, we have a logical KV cache blocks, physical KV cache blocks, and block table. First we'll allocate the space and store the prompts KV cache. As you can see here, all the prompts are divided and stored in the logical and physical KV cache blocks. And if we look at our block table, we can find that our pages, all these pages are stored in the physical block number 7. Just by looking at this block table, we can understand that where our data is stored. So that's basically what we do. When we store the KV cache, we use this method, and to access the data, we use this block table. So that's pretty simple. And when we generate the next word by the AI, and it will stored here and also in the physical KV blocks, and our block table got updated. We can see that in the previous one our filled slots was 2 and now it's 3. So our 3 blocks is filled, or slots is filled. And when the new prompt is generated, the data stores just like that. You can see when the new prompt mathematician is generated and our block table got updated, and here we can see our 4 blocks is filled. And when the next one came, which is renewed, it allocated space for that prompt automatically or dynamically in our physical KV blocks. And our block table is also got a new value, which is our renewed our renewed is stored in the physical block number 3. So here the main thing is our block table. We can find or access the data by looking at our block table. So when we need the KV cache, we can simply look at this block table and fetch that value easily. So we use these techniques to prevent the memory waste in KV cache. So that's what happens inside page attention. Now let's talk about another mechanism used in vLLM, which is continuous batching. We use continuous batching to speed up the generation process. So first let's understand this image. So here we have T1, T2, T3, T4 up to T8, which represents the time complexity. And we have our yellow blocks, which means our input prompt. Then we have some blue blocks, which represents the generated token. And then in the end, we have a red one, which shows the end of generation. Okay, so that's it. Now, before we talk about continuous batching, let's understand what a static batching is, which we used in the traditional LLM. So, batching in large language model means processing multiple input requests together in a single forward pass of the model. So instead of running the model separately for each request, we group them and feed them to the model at once. So here that's what happening. We have our times here, and this is a first prompt, second prompt, third one, and the fourth one. In this image, all of the first prompt of all these input are created, and here in the batching technique we give the a set of input together, right? So if one terminated or ended generation early, it needs to wait for the others to end too, which means the memory or the GPU can't utilize these blocks, and it needs to wait for the others to end. So these space are getting wasted. Okay, that's the problem of static batching. Here we can see our S3, the input prompt 3 is terminated first, and the first one is terminated second, and the last one terminated third. And but all of these terminated early, but all the left out blocks needs to wait for this one to finish, the second one to finish, because that's how batching works. It gives a set of prompts to the GPU to make the generation process. So we cannot use these spaces, and it's a waste of time. So we change this or overcome this by using continuous batching. So just by looking at this image, we can understand that what's happening in continuous batching. Here left shows the batch after one iteration, and this image shows the batch after several iterations. As soon as first prompt's generation is ended, the next one kicks in. So it doesn't needs to wait for the others to finish. Okay, it doesn't works like the batching techniques before. So that's what happens inside a continuous batching. Here we get a higher GPU utilization. The GPU starts a new sequence immediately, not waiting for all to finish. So that's a big thing. So that's it, and I told you guys that if you stay till the end, I'll show you an example of how we can run vLLM in Google Colab. So here first we just install our vLLM using pip, then we also install our Hugging Face because we need to use the model, and then we'll log into the Hugging Face using our API key, then import our vLLM, then we'll put the model here and put it into a variable, and then we need to give the prompt, which is the capital of France is. After that, we'll just call LLM.generate prompt. It will generate the prompt. It's just simple as that. And for printing, we can use these two lines, which only took our output prompt. Here we can see the Paris. So this is our output prompt, this is our input prompt. So the capital of France is Paris. That's it. It's done. So it's just simple as that. You can run this in your own devices if you want. So that's it, and I hope that you get a basic idea or a clear idea of what vLLM is and why we should use it. And if you like this video, please give it a thumbs up and subscribe to my channel. I will upload these kinds of videos. Let's keep it in touch and bye.